Okay, at this point, we have talked about the real problem in reinforcement learning. Um, we have talked about the value functions for the state value function and the action value action function, but we haven't talked about uh, how to solve this problem, how to find the maximum or the optimal policy to solve the problem, which is the real problem here. So here we have three different approaches. So the first one is dynamic programming, Monte Carlo methods, and temporal difference learning. So what are dynamic programming?
Yeah, actually, these three elementary solutions methods.
Okay.
So dynamic programming is based on model. You remember that we find a transition matrix probability
Yes.
for
For
the
example, of the class.
yeah, for
The course.
example, the class 1, 2, 3, basically, or go to sleep. So dynamic programming methods are well developed mathematically, but require a complete and accurate model of the environment. Monte Carlo methods and temporal difference learning, they are not based on the model. They only need the interaction with the environment to make the algorithm. And well, this is the definition, but I'm going to explain better in
Example.
an example. So, for example, this is a Markov decision process. So we are in a certain state, and we can take some actions, and we arrive in another state. So in the time t, time plus 1, plus 2, plus 3. So the the dynamic programming, they take care. Well, they the algorithm is based on model because they make a average over all the possible actions that the policy take in one step. For example, in this can take different 4 different actions.
So he has to look for all the possible options he has.
Yeah,
Just to make an
and
exploration, total exploration.
yeah, not really, really, but only one step.
Okay.
They take account the reward for this action and reward for this action, and they multiply by the probability to be in the state t, pass to the state s prime. That is the next. And that is dynamic programming. Monte Carlo methods, how the name tells us, is a sampling for uh, a total episode. So an episode is something that we're starting in a certain state, make action, go to a state, action, state, and finally, in most of the cases, we final the process. We stop when we win the game or when we lose or something that tells us that this is an episode. For example, in this case, this way can be an episode, or this another way can be another episode, and this is the terminal state. So the Monte Carlo approach, uh, they make um, different samples of episodes from these three. He um, measure or calculate the returns, the commodity returns, and the idea behind that is to make an average of all these return for all the samples. And temporal difference learning, that is in this case, is a sort of kind of combination. Remember that I said, programming only take one state into account, and Monte Carlo take all the episode. That is something computational expensive. So temporal difference only take one step that is like a bootstrap from Monte Carlo, but have something similar to dynamic programming. So the first, or one of the most important algorithms in reinforcement learning is the Q-learning.
Okay.
Yeah,
And what is this?
this is temporal difference learning. Is a off policy. I'm going to explain that later. And the way that the Q-learning function make the actualizations is based on this equation. So in is we are in the state st and we take the action at, we we are going to actualize it with the same plus step size and this amount. But this amount is something interesting because this part, this part, and you remember that this is one of the relations that the Q function has.
Yes, with the return one step ahead and the building function for the next steps.
Yeah. So this is for part of the Bellman equation actually, and this is the target mm, Q value minus the last.
The old value.
Yeah, and that is sort of kind of error, you know, and that take steps until this error is minimized, minimizing, and when the algorithm,
Converse.
yeah, they approximately found a optimal action value, action value function. Another one, something similar. In this step, we take the maximum for all the possible actions, you know. And another is the SARSA, the state action reward state action. This also a temporal difference, but it's really similar. Only we in this part we don't take the maximum over all the actions, but we make you know, like a sample of the possible actions. We make an action a sample of the state and the action, and we evaluate here. So the difference between the Q-learning that is a off policy and SARSA that is a on policy is that the in SARSA learns based on the performance of the current policy. What that means? That means this is kind of the policy improvement. So we're starting with some starting
Value. Value function
value function. Well,
with
it can
a
be
policy.
the B function or Q function, whatever. And we define a policy. Maybe it can be the random policy.